Okay, guys, now we can continue with the lecture. If you remember, we had gone through the steps of this generalized AM process chain. We do the design, we do the conversion, we import this STL model to the CAM software, we do the settings, we build our part, we remove it simply, do some post-processing operations, and then finally use it in our specific application. But we said that there might be some little differences between different additive manufacturing technologies. Some of them might be eliminated, or in some of them you may have an extra steps. But usually they have almost the same steps, more or less the same. And now let's have a look at the first example, first type of additive manufacturing method. For the polymer-based systems, in the systems we are using liquid photopolymers first, and then with the help of the laser or light sources, we cure and try to solidify the parts. Here's an example, for instance, a bunny. This is fabricated by using SLA technology, a technology using photopolymers. As you see, it has some special support structures. And it's not that difficult to remove. By using your hand, applying some force, you can remove it. And it's quite easy to use. The supports are generated in an automated manner, and its accuracy is much higher if you compare with other technologies. And you may have a look at my ring, for instance. Here, this blue one is printed on an SLA system. It has many features, and this is actually used for investment casting. The jewelry industry, they design such difficult parts. They print it by using photopolymer technology, photopolymer-based systems, printers, and then they prepare a mold for it. They evaporate this mold so that there will be a cavity inside the plaster, and then simply pour the metal they are looking for, gold or silver, is up to their design. But the accuracy is much higher, and that's why such industries are using the systems, these photopolymer-based systems. But in the earlier days, the material properties weren't that good, and with the help of the improvements in material science, now we have much better materials, and we can use all of them on the SLA type of 3D printers. Their temperature resistance has been improved, their strength are much better, they have nice ductility. Then we have some powder-based systems. In powder-based systems, we use obviously, as the name implies, a powder bed, and we don't need to have special support structures, especially for plastic ones, for polyamide case, for instance. But if it's a metal, and if it's using powder bed, then still we need to use some support structures. We will discuss these details once we are spending some time on powder-based systems. And the advantage of them is that you can have full color prints, which means that in the design and fabrication pipeline, at some point, you need to define the colors of your part. But obviously, we know that it's not possible with STL. So you need to have maybe an AMF file or a specific file of the printer you are using. Another advantage of the system is you may use these powders once again. You may have 2 portions from the recycled, but at 8 units of your powders should be Neve powders. We will discuss all these. These are just an introduction, and we are briefly discussing the design and the fabrication pipeline, the variations in the pipeline. But as we have seen up to this point, there's not much difference, almost the same. Your design, convert to STL files, send to the machine software, do some settings and print. But obviously, if your printer has many capabilities like color printing, you need to have an extra step like coloring your design or doing some modifications on your design. In the extrusion-based systems, again, we need to have support structure. This is an output of an FDM or FFF system. We need to have, again, support structures. In the earlier days, we had a technology called thermojet, but right now we don't have it. And we will be mostly discussing fused filament fabrication systems while discussing the multi-material systems. And here, the field patterns, the interior field patterns are much more important. And in the setting step of the fabrication pipeline, you need to spend more time on selecting the appropriate patterns for your part. And sometimes we can consider them as the strongest polymer technology. For the metals one, obviously we have better technologies, but for the thermoplastics, fused filament fabrication is one of the best approaches. And obviously, we need to have a kind of support structure removing operation in the 7th step of the pipeline. You need to remove these support structures and do some maybe cleaning, some polishing. And you see here some interior filling patterns. You may have such very simple ones, linear hexagonal ones, or such Morgenstern, cat fill, or shark fill. But the main thing is that we need to have some material, some structured material interior so that the part will be stronger. If you have nothing inside, if you don't have such structure inside, then by applying some force, you can easily break your parts. Then we have some solid chips based additive manufacturing methods or laminated object manufacturing. The advantage of these methods, these technologies is that you don't need to generate such special support structures. We will be discussing the details, but right now we can say that the 4th step of the pipeline is simplified. You simply import your design, and then with default settings, you can go on. You don't need to spend time on selecting the regions where you need to have support or selecting the type of support structure. This is not valid for laminated object manufacturing. And we can easily actually recycle these automatically generated support structures. We will discuss them. So it's more sustainable than the other ones. And considering the metal ones, this is a bit complicated. We need to use such substrate. And we start building our parts on the substrate. This rectangular block of material can be considered as a substrate, and you start building your parts on it. And later, after the part is fabricated, you need to do some wire EDM or do some sewing operation and try to remove your part from the substrate. So in metal systems, the pipeline is a bit time consuming. You need to spend more time on post-processing. In other case, you may have more temperature gradients and there might be warpage, some residue stresses remaining around. You need to be aware of them and, as I said, spend time on having better products, and you can do it by adjusting the parameters. So you need to spend more time on the 3rd and the 4th steps. And even some cases, you may do all these steps and still cannot get a high quality product. If that's the case, you should start from scratch. Modify your design and modify the parameters so it will take more time on the metal systems to get a high quality product. And in the previous slides, I said that if you are using polymers in the powder bed systems, most probably you will not need to have support structures, since the powder itself, powder inside the bed, actually will act as a support structure, and you don't need to have such special support structures. But if it's a metal product, if you are using metal powders, then you may still need to use supports for actually better thermal properties for heat dissipation, you need to have such support structures. And considering the energy density, if you want to use metal powders, obviously your laser system should have more power to give more energy to your powders so that your temperature will be much higher and they will be melted and join easily. So it's quite difficult to construct such a metal 3D printer. And another issue is that the weight of the parts and the weight of the machine is much higher once you are using the metal powders. Another issue is that you may have some optimization and try to have much simpler products having some organic structures, but they can be manufactured by using such powder-based systems. And if you want to decrease the weight of your overall product, you may use titanium powders, but it's obviously an expensive powder, and they are mostly utilized for aerospace industry to decrease the weight of the products. And the accuracy in metal systems is not higher. If you look at the top surface of this one, we have high surface roughness, and you need to do some post-processing. Even if you look at this one, it's again a metal part, but still have high surface roughness values. If it's an important issue, if you want to have very low surface roughness values, then you need to do some extra processing to have good part density and part accuracy. So you may do machining or shot peening. Again, it depends on the application you are going to use that part. And especially if it's a kind of an assembly, part of an assembly, the mating parts become an important issue. They should match perfectly, otherwise your assembly will not work, will not function, and you need to do some further machining operations. The speed of the systems are a bit slower since we have high temperature systems, and we need to be careful, and there are many safety functions, and you need to wait maybe some time after a layer is completed. So that's why it takes more time compared to an photopolymer system. So you have some heavy requirements on the amount of energy actually disposed on the powders, and we need to handle also these powders properly. We need to spread them in a high quality manner. The thickness of the layers should be as uniform as possible. And the powers of the lasers are usually around 100 watts, maybe more than that, but it's obviously less than hundreds for the polymers, for polyamides or for other types of thermoplastics. So how we are going to maintain the quality of the equipment? Obviously, we shouldn't be operating them in dirty or noisy environments. We may have some special rooms, especially for metal systems or some for powder-based systems. And the humidity is a problem, so you shouldn't be storing your materials in high humidity regions, rooms. You should consider them, otherwise you may have some less quality products that might be cracks on the surface or inside the part, and once you use them in your end products, you will probably have problems. So you may perform some regular checks on the material quality on maybe some parts of your additive manufacturing machinery. And at some point, from time to time, you may print some test parts and check whether your printing equipment is functioning properly or not. They're very similar to the test patterns we have in the paper inkjet printers. And maintenance of the lasers is quite expensive, so you should be careful while you are using such laser-based systems. Another issue about the head of the printers is on the nozzles. If you are using fused film fabrication type of systems, from time to time you may need to change your nozzle since it may be clogged, and you may have some particles at the tip of your nozzle, and you may not be able to extrude material. As I mentioned, materials usually are prone to humidity, so they have limited shelf life, and you shouldn't you should have more, let's say, moisture in the environment. You shouldn't expose them to light, especially if you send photopolymer material. If it's under, let's say, sun, then you may be photopolymerizing or curing the photopolymer. So light shouldn't be actually reflected on your photopolymer. And mostly we have inert powders, but again, you should be careful and you should consider the warranty issues of these materials, and you may replace maybe them after some amount of time has passed. And we have another issue related with the extrusion systems or fused film fabrication systems. The diameters of these filaments are quite important. If you have variations in the diameter, then you'll probably have problems in the end product, since the settings are actually done according to a specific diameter, and the slicing software or the patch generation software is assuming that you have a constant diameter. So if you have variations in the filaments, then in the end product, you will have some extra material or low material in some regions. Any questions, guys, up to now about the variations in some additive manufacturing systems and some fundamental issues about maintenance for materials, maintenance for the machine? No questions, okay. And I will briefly talk about some design for additive manufacturing. So while you are designing some parts to be built in with the help of additive manufacturing system, you should be careful about the orientation you are going to use in the fabrication. So most probably, if you design such a bunny, let's say, you'll be printing in that direction, and you should be careful about the regions where you need to have supports, especially the regions on of the head, the ear region. Actually, we have shallow angles there. So you may, if it's a new design, you may modify the ears so that the ear angles are higher than 45. If that's the case, then without using any support structures, you may be able to complete your design and fabrication. So the orientation and some angles on your design are quite important, since you'll need to spend time on the support removal. We will spend more material for the support structures. Another issue, especially if it's a photopolymer system, we don't need to use completely filled products. If you consider this bunny, I printed it by using an SLA system and photopolymer system, but I didn't hollow it out. The interior of this bunny is completely filled with material. It's not a good solution, good approach, since photopolymers are quite expensive. So it's better you do some hollowing out and try to decrease the amount of material we are spending for the fabrication of this part. And also, as I mentioned, you may consider some difficult regions. You may try to modify your design so that without using any support structure, without using any extra material, we should be able to print, we should be able to fabricate the same product. Or if it's an assembly, again, you should be careful so that you will have a perfect match between the parts. You may consider the shrinkage phenomena and try to have the final dimensions as good as possible. Another case is that in your initial design, you may have multiple parts. But if it's possible to join them before the fabrication, please do it in the design stage. With that approach, you will be spending less time on assembly and less time on fabrication. In a single print, you may be having all these parts together and you'll spend less time on removing, less time on the preparation of your fabrication. And lastly, since additive manufacturing has many capabilities, you may embed some information, some markings on your design so that you don't need to do it later. You don't need to do maybe stamping, since the information will already be printed on the part. So here's an example, for instance. This is the initial design. We have such a part, a very weird shape. If you do not perform any segmentation, if you do not change your design, then you will use that amount of material for the support purposes. Since this is the upper part, if you design and fabricate it in such an orientation, then we need to have support structure underneath these regions. Otherwise, they will be falling and the quality of the underneath surfaces here will be much less compared to a different orientation. So what we do, instead of this complicated shape, we divide it into two parts. As you see here, without using any support structure, we can print these two parts. And the thing is that later, after the parts are produced, we need to join them by maybe using a specific type of glue here or a specific type of maybe shrink fits. It's up to you. And again, it's better to do it with shrink fits. Otherwise, the user will spend more time on finding the appropriate adhesive and he may not be successful. So it's better we have a kind of a shrink fit and try to fit these two parts together in an easy manner. And with such an approach, we will be using no support structure. So I can say that this will be printed with less material and in a shorter time. Since if you look at the height of these two parts, it's up to here, but the height of this product is up to here. So with less layers, we can handle the fabrication. So in summary, by using less material and spending less time, we can produce the same part. And this is done actually with the help of the design. Once you do your design according to the principles of additive manufacturing, you will gain time and material. Another question, guys? Here's another nice property of additive manufacturing in terms of design. This is somehow related to one of the project topics, embedding some information into the design. So this is our original design. As you see, if you do not spend extra time, you will have no information on this part. This is a conventional printing, but you cannot actually acquire any information. So what is done here is that they have a special kind of a patterned bottom surface. They have some kind of a coding scheme, and they have such grainy surface. And then once they fabricate and do some scanning, these are their scanners. Once they scan the surface, and with the help of their decoding algorithm, they can decode some information. They can get the name of the product, some other information about this product, maybe who designed it and what type of application is going to be used. So this is only possible with scanning the bottom of this part and doing some decompression operation. So it's a nice way of embedding some information into the products. This is not an QR or another barcode, but with the help of the patterns on the bottom surface, they manage to store information. Any questions, guys, about these examples?
Hocam bu texture'ı nasıl desem tasarımda mı yapıyorlar yoksa kullandıkları tablonun tekstürünü mü alıyor?
No, they are doing it while designing the part.
Peki mümkün olur mu? Mesela bir tekstürlü bir tabla koysak onun üstünde eriyik bir şekilde dökülüyor ya onun kalıbını alır belki ilk katmanda. O tarz bir şey mümkün olur mu? Mesela her parçada farklı bir tabla koysak hangi kodu yazmak istiyorsak tarzı.
Yes, it's doable, but I think it might be more complicated since you need to have texture for each part. With that approach, they don't have a specific table, and they were using jetting type of additive manufacturing system, not FDM, not fused flame fabrication. So they were able to actually print such grainy surfaces. If it's an FDM, it will be quite difficult to actually have such grainy and structured surface. But as your friend points out, you may have a specific, let's say, table, maybe like this one, having some holes or maybe lines, some grooves. Once you extrude material, the material might be going inside into the holes and into the grooves. And once the print is finished, you may remove it and see a specific pattern underneath. But as I said, you need to change this pattern for each part. If it's a serial production, then no problem. Underneath of the part, you may have some specific signatures, specific information. Yes, it might be a good approach. Another thing, you may print the pattern by using another printer or by using another, let's say, material which can withstand to high temperatures, so that it might be the mold of your next print. Any other questions? Kian, do you have another?
Yok, teşekkür ederim hocam.
You're welcome. So it's a nice way of storing information. If no questions, then I can continue. So let's have a look at some non-conventional CAD modeling. Sometimes it might be difficult to design a specific part. So what we do some kind of scanning, and this is usually done in medical industry for medical purposes. We have computerized tomography. We have some slices there. Once you have the slices, and by using some specific CAD tools, you may join these slices and try to have a 3D CAD model. And this might be also the same case in magnetic resonance imaging, MRI, or you may have ultrasounds. Some information might be coming from ultrasound technology, and we may use these raw data and try to obtain a 3D product. But obviously, we need to do some considerable amount of processing. So your software should be powerful, your computer should be powerful enough. And we have such software. The most popular one is called as Materialized. And in medical industry, if the people are actually wanting to print their products by using the information coming from CT, MRI, or ultrasound, they usually use Materialized software and try to generate the CAD files, and then later transfer this CAD file to the CAM software they are using for the production. Or we may simply do a reverse engineering operation, do some laser scanning from the outer surface and try to obtain the 3D product and then later print it. We may also do it for architectural modeling. We have some large laser systems. You may scan the whole architecture, whole, let's say, structure, and then try to print some small replications of these architectures. So we have some further discussions about these issues. In the complicated, let's say, CAM software, you may focus for a specific region and just work on that region. Instead of setting the properties for the whole layer, you may set some specific properties for a specific region and then try to print your part accordingly. So for that purpose, we need to have more intelligent systems, more complicated systems, so that we can do some segmentation on the part and have an maybe high resolution at a specific part and low resolution on another part of the same product. But obviously it's not easy. We need to have complicated software and complicated machines. But in near future, I think we will have such commercialized systems, such hybrid technologies using such approaches.